This is the last section for this unit. It involves kind of a cool way of taking the derivative of really complicated expressions. So I've given this one 3 different titles. Taking complicated derivatives using the laws of logarithms. I usually call it logarithmic differentiation. It's a technique used to take the derivative of expressions that are really hard to take the derivative of otherwise. Or my cool nickname for it is the ultimate nullifier. So it takes really hard questions and gives you like superpowers in order to take their derivative. So in order to do this technique, you need to remember the laws of logarithms. And I've given you 2 logarithms here with complicated arguments. And I wanted to remind you how you can take those and separate them using the laws of logarithms. So let's take a look at this one right here. And we have a product in there, we have a quotient, and we have exponents. So as we break that up into several logs, it should look like this. 2 log of a to base 2, I use the down and front rule, plus 3 log of b to base 2, down and front rule, product changes to a sum. And then the quotient minus 3 log of c to base 4. In this example here, it's ln, which is the natural logarithm. The rules apply exactly the same. 3 log x, 3 ln x, 3 ln x, remembering this square root symbol represents the fractional exponent 1/2, plus 1/2 ln x squared plus 1 minus ln cosine of x, like that. So what's really good about this is that we're taking products and quotients and expressing them as sums and differences. And taking the derivative of sums and differences is a lot easier. So here are 2 questions, typical questions, that we will deal with in this particular section. So number 1, we have just a function y equals, no logarithms in it yet, and it's equal to this complicated product with chain rules and exponents. So this is a double product rule. To take the derivative right now would be really hard, lots of hard work. So what we are going to do is we're going to use logarithms to help us change this product, this double product, into sums and differences. That's the benefit. The cost is that it's going to change from a y equals function to a ln y function where we're going to have to do implicit differentiation. So let's give it a try. We're going to take the ln of both sides, and that allows us to take this product and change it into sums and differences using the laws of logarithms. So let's break this one down using our laws of logarithms, and it would look like this. 3 ln x plus 5 ln x to the 4th plus 7 plus 8 ln 2x plus 5. Bad news is we took an explicit function and changed it into an implicit one. The good news is this difficult product is now a sum and difference. So as we take the derivative of this expression, it will look like this. The ln of y becomes 1 over y times the derivative of the argument dy over dx equals, and all of these are easy to take the derivative of now. 3 times the derivative of ln x, 1 over x, plus 5 times the derivative of ln x to the 4th plus 7, 1 over x to the 4th plus 7 times 4x cubed, plus 8 times 1 over 2x plus 5 times 2. So easy to take the derivative of that sum or difference. No product rule, quotient rule type things required. Now we're going to take both sides and multiply them by y. So we're going to imagine multiplying both of these sides by y. This y will cancel with this y, And you've already simplified it down to dy over dx equals, we have this blue y here, times this bracket, 3 over x plus 20x cubed over x to the 4th plus 7 plus 16 over 2x plus 5. So we're almost done this question. We just want to be reminded of what it equal to originally. It wasn't an implicit function. It was y equals x on the right hand side, an explicit function. So we want to take and substitute this in place of y. So your last line, a little bit of writing. Dy over dx equals x cubed, x to the 4th plus 7, all to the 5th, 2x plus 5 to the 8th, square bracket, 3 over x, 20x cubed over x to the 4th plus 7, plus 16 over 2x plus 5. And that's all that we're doing today. Taking a complicated expression, taking the ln of both sides, differentiating implicitly, and then substituting back for this y. Just 2 more examples that we'll look at today. Here's one right here. Complicated argument, products, quotients all in it. Really hard to take the derivative of. So let's use the ultimate nullifier. Let's use the logarithmic differentiation technique to take the ln of both sides and separate it. So we have ln y equals 4 ln x plus x squared ln e. This is special, we'll talk about it in a moment, plus 2 ln 3x minus 4. Gonna be tight on space on this one. Minus 2 ln cos of x. So now it's a implicit differentiation. Let's see if we can do it. Ln of y, this derivative becomes 1 over y times dy over dx equals, and the derivative of 4 times ln x is 4 times 1 over x. Remember that ln e has a value equal to 1. So this is really just the derivative of x squared, which is 2x, plus 2 times the derivative of this expression, 1 over 3x minus 4 times the derivative of the argument, minus 2 times the derivative of ln cos x would be 1 over cos x times the derivative of cos x, which is negative sine x. So let's take and multiply both expressions by y, and we do that so that we can isolate dy over dx. Now we'll have these y's cancel, this y with this one, and we're left with dy over dx equals y times 4 over x plus 2x plus 2 times 3 is 6 over 3x minus 4. And this is an interesting one. We have this minus sign times this minus gives us a plus 2 sine x over cos x. So we'll go back to that last part of it, which is that substitution. Remember, the original expression looked like this, so we can substitute this in place of y down here. And you've got dy over dx equals x to the 4th e to the x squared, 3x minus 4 squared cos squared x times the square bracket, 4 over x plus 2x plus 6 over 3x minus 4 plus 2, and we're going to simplify this tan x using trig identities. The last example that I'm going to show you is one where we don't have any rules to take the derivative of. We don't have a rule where you have x as the base and x as the exponent. So we have to use this technique here. In the other previous examples, it was really a convenience to take a difficult question and make it easier. Here, it's a necessity. So we're going to take the ln of both sides so we can use the down and front rule. And you get ln y equals x cubed times ln x. Now that's a product that we can't get rid of, so we're going to take its derivative, and its derivative would look like this. The ln of y, its derivative becomes 1 over y times dy over dx equals, this is a product, let's use the product rule first, x cubed times the derivative of the second plus the second ln x times 3x squared. Multiplying both sides by y so that we can cancel this y with this y. You get dy over dx equals y times, this simplifies down to x squared plus 3x squared ln x. So quite a bit of simplification we can do here. There's a common factor of x squared in that, and we're going to replace y with x to the exponent x cubed. So dy over dx equals y, which was x to the exponent x cubed, times the common factor x squared times 1 plus 3 ln x. Well, these have a common base of x squared. We can add their exponents. Dy over dx equals x to the exponent x cubed plus 2. Multiplication of like bases, we add the exponent. All multiplied by 1 plus 3 ln x. So box that up. That's your simplified derivative. Now let's see what else the question asks. Find the equation of the tangent line at x equals 2. So at x equals 2, y would equal 2 to the exponent 2, and this 2 is cubed. So that gives you 2 to the 8th, which is 256. So your ordered pair is 2, 256. And now let's see if we can figure out what the derivative will be at x equals 2. dy over dx is going to be 2 to the exponent 2 cubed plus 2, that's the exponent, all multiplied by 1 plus 3 ln 2. So that equals 2. 2 cubed plus 2 is 10. 1 plus 3 ln 2. So the value of the slope, dy over dx, is equal to 2 to the 10th is 1024 onto 1 plus 3 ln 2. And hopefully you remember the rest of the routine now. We want to find the equation of the tangent line, it says. Here is your x1 and your y1. Here is your slope. So we're just going to plug those values into this formula. That should be x1 and y1 like that. Y minus y1 equals m onto x minus x1. Y minus 256 equals m. 1024. 1 plus 3 ln 2 times x minus 2. So y equals 1024, 1 plus 3 ln 2 times x minus, and I'm just distributing this in here, 2 times 1024 is 2048, 1 plus 3 ln 2, and then we'll transpose that plus 256. So that's a crazy equation of a tangent line. The tangent to this really complicated expression. We didn't have techniques to take the derivative of that before. Now we do. Last video for this unit. Have a great day.